This conference will now be recorded.
Good morning. Today our topic is tunnel diode. Tunneling means highly doped material. Tunnel diode constructed compared to the ordinary PN junction, 10 power of 12 percentage doping concentration is high. So tunnel diode explanation with respect to layers. Example, everyone know every material has 3 layers: valency band, empty energy gap, and conduction band. Here tunnel diode characteristics. Okay, tunnel diode has 3 layers. This is P-type material. Here N-type material. And EC for conduction band. EG, empty energy gap. And EV for valency band. In valency band, P-type material, majority holes. In N-type material, majority electrons. From valency band. This is EC, EG, and EV. Before biasing conditions, I am taking here only 5 free electrons. N-type material, here P-type material. Okay. Now, this is without biasing energy band diagram. With biasing, all majority of electrons tunnel into N layer to P layer with respect to band. This is without applied voltage. Now, with forward bias condition, tunnel diode forward bias, tunnel diode forward bias. Okay, tunnel diode equivalent symbol like this. In forward bias, one resistor, ammeter in series, anode connected to positive potential, negative connected to cathode, and voltmeter across junction, ammeter positive potential, negative, voltmeter positive, negative connected to cathode. In forward bias condition, now with respect to energy gaps, energy band diagram, EV, EC, in middle one is called empty energy gap, EG. This is N-type material, here P-type material. See, all volts available at valency band in P-side material, and with biasing, all electrons available in N-side valence conduction band, EC. This is first connections. Now, with the applied voltage, with the biasing, same diagrams. This is empty energy gap. Here free electrons in N-side. Here free holes in P-side. One point is very, very important. Free holes at valency band. Here free electrons at conduction band, EC. So whenever applied source connected to the across the diode in forward bias only, immediately tunnels start from N layer to P layer. Here one more important, N layer conduction band, P layer valency band. So at microvolts only. Understood? In microvolts, whenever we have applied very, very little voltage, micro milli nothing but less than 0 volts, suddenly tunnels start from N-type conduction band to P-side valency band. In second condition, if you want to apply more than millivolts, here layers with this conduction band going into the upside, now Here number of holes after applied voltage. See here, first we have two rows, 1 and 2, quite opposite side valency band. Whenever we have applied voltage, this EC from N layer move into the upside. So here doping, tunneling will decrease. Whenever applied tunneling is high, here how many? Two layer of inside tunnel to the opposite of valency band. But here after applied more voltage, more than 0 means 0.1, 0.2, this valency band is comes to down from P type, but N type condension band move to the upside. Now here only few electrons tunnel into the P layer. If you want applied more than 0.1 volts, quite here valency condension band opposite side has empty energy gap. This is EC, here EV, this is EG. So complete current going into the 0 means current from millivolts to 0.1, 0.2 volts, current going into the decrease. After more than 0.7 volts, more than 0.7 volts, more than 0.7 volts, quite opposite of here all valency, condension band electrons jump into the condension band of P layer, direct tunneling to condension band. Now EC to EC, from N layer to P layer. Okay, this is the tunnel diode forward bias characteristic. So according to this graph, see at millivolts current is rising. After more than 0 volts, currents come to down. After 0.7 volts, again current comes to the increase. So it has three regions. One is negative resistance region. Here current is decreasing. This region is called negative resistance region. And this condition, maximum current done by maximum tunneling. This is called tunnel current. Okay. And disadvantages, advantage of tunnel diode, advantages tunnel diode. Number one, long life. Tunnel diode life is long. and high speed operation. First one is long life, and the second one high speed operation. High speed operation. And the third one low power consumption. Low power consumption. And disadvantages. First point, tunnel diode cannot be fabricated in large numbers. Cannot be fabricated in large numbers. And second one, being a two-terminal device, the input and output are not isolated from one another. That is the second disadvantage. And applications, number one, tunnel diode are used in logic memories. Logic memory storages. Second one, tunnel diode are used in relaxation oscillator. Relaxation oscillator. Third one, tunnel diode is used as a ultra high speed switch. Ultra high speed switch. And fourth one, tunnel diode in FM receivers. Okay, this is tunnel diode construction, operation, advantages, disadvantages, and applications. Okay.
This conference will now be recorded.
Varactor diode. In a PN junction, very thin deflection region acts as an insulator of the order of 5 into 10 exits on either side of the P and N regions, and it separates the P and N regions or acts as conducting plates. As a result, this capacitor is formed. The capacitance may be varied by varying the reverse voltage applied to the diode. The Varactor diode, also known as VVC, nothing but voltage variable capacitance. Voltage variable capacitance. In other words, the Varactor diode is a semiconductor, voltage dependent, variable capacitance. Their mode of operation depends on the capacitance that exists at the PN junction when it is reverse biased. In reverse biased, Varactor diode acts as a variable capacitor. The depletion region in a PN junction forms a barrier which separates the positive and negative charges on the opposite plates of the diode, and the depletion region acts like a dielectric material. As PN junction possesses junction capacitance. The transition capacitance CT established by the junction is determined by CT, CT, C for capacitance, T for transition is equal A by eta permittivity, this one, by width of the junction, where eta is permittivity of semiconductor material, eta is permittivity of semiconductor material, and W D is equal the depletion width, width. This depletion width varies with respect to reverse voltage. As the reverse potential increases, the width of the depletion region increases, which in turn reduce the transition capacity, because CT inversely proportional to WD. In terms of the applied reverse bias, the transition capacitance is given by CT is equal K by VT plus VR whole power of N. Okay. Here K is constant and VT means knee potential, nothing but curtain voltage. Knee voltage. You know silicon knee voltage is equal to 0.7. Here silicon knee voltage is equal to 0.7. Germanium knee voltage is equal to 0.3. And VR is reverse voltage. VR means reverse applied voltage. Reverse applied voltage. Okay. Here N for small n is equal to 1 by 2 for alloy junction, and n is equal to 1 by 3 for diffused junction. Here alloy nothing but in forward bias, reverse bias. Here diffuse means forward bias. And Varactor diode equivalent symbol, same diode, but here it's act as a variable capacitor. Anode, cathode. This curve nothing but negative potential. Straight line means positive. So this is equivalent of variable capacitor, and its equivalent circuit RS R. RR means reverse resistance, and it acts as a variable capacitance. CT, transition capacitor. Here R, yes. RS nothing but source resistance. RR means reverse resistance, reverse diode resistance. Here CT for transition capacitance in reverse bias. Okay, when the reverse bias voltage decreases, the deflection layer narrows to down. This decreases the electric thickness, which increases the capacitance with respect to our equation. See here, CT inversely proportional to VT plus VR, and this indicates that the variation of capacitance is maximum when the reverse voltage is equal to 0. If you want to increase reverse voltage, capacitance will be decreased, and in this diode the variation of capacitance are controlled by method of doping in the deflection layer, or the size and geometry of diode construction. There are two types of doping used in Varactor diode. First one is abrupt doping. First one is abrupt doping, and second one is hyper doping. And advantages of Varactor diode. Varactor diode. Number one, smaller in size. Smaller in size. Number two, rugged and reliable. Third one, no movable part. And fourth one, operate over wide range of frequencies. Fifth one, it has fast response. It has fast response, and electrical tunneling applications. electrical, tunneling applications, a large range of capacitance variations. These diodes are used in some of the high frequency areas like frequency modulation. Frequency modulation. Example, in television tuning. Television tuners designed by Varactor diode only, and FM radios. FM radios. Second one, in automatic frequency control circuits. Automatic frequency control circuit. Frequency control circuits. And the third one, adjustable band pass filter. It's used in adjustable band pass filters. And the last one, in parametric amplifiers. Parametric amplifiers. These all are application of tunnel diode. Varactor diode. Varactor diode every time used in reverse bias only.